Okay, so in this section, you guys, I'm going to teach you a new technique of graphing. We're going to graph functions using what are called transformations. So the goal number one is exactly that, to graph functions using transformations. A transformation can be any one of several things. It can be a translation, which is a shift of like a parent graph, or a base graph, as I'll call it. You'll end up reflecting across axis, either the x-axis or the y-axis. You'll end up stretching or shrinking a given parent graph by a certain factor. That's goal number one. Goal number two, we're going to identify even and odd functions using the even-odd function test. What you want to do is you want to think about a parent function or a base function. And the base function you get by stripping away whatever you're adding or subtracting to x inside the parentheses. On the outside of the squaring function, the exponent of 2, whatever you're adding or subtracting, delete that. And even out in front, delete the thing in front. So in other words, delete the -2, delete the -1, delete the -3, what's left? X squared. You can't delete the exponent of 2 because that really changes the shape of the graph. It's not going to be a parabola anymore if you delete the exponent. But everything else you delete, and you come up with the most basic quadratic function you can think of, y equals x squared, or the parabola, very basic parabola. Okay, I don't want to cross all those out. Let me erase that. Okay, so the parent function or base function is just y equals x squared. That's what you get when you delete the -2, the -1, and the -3. Now the idea with using transformations is, isn't it way easier to plot y equals x squared than the given function f of x? By just plotting points with your t-chart, isn't it way easier? Sure. So we're going to plot, if you want to call it step one, we're going to plot the base function, which is y equals x squared. You know, I could do that from memory, but if you don't remember, if you haven't taught this for 20 years, which you haven't, maybe you don't remember. So let's go back to plotting points. So what are some good values to plug in for x?
1, 2,
there you go. 0, 1, 2. And then don't be prejudiced against negative numbers. Plug those in too, right? All right, and then the y equals x squared is called the squaring function. To get the output, just square all the inputs. So what do you get? 4, 1, right? You square -1, you get 1. Square -2, you get 4. What do you get when you square 0? 0. Square 1, you get 1. Square 2, you get 4. All right, I think we can plot those points. So 0, 0, 1, 1, -1, 1, 2, 1, 2, 3, 4. -2. And then draw, since you don't have different colors, draw it using a dashed curve. Because this isn't your final graph, is it? In fact, I think I'll do it using dashed. Or dotted, whatever you want to call it. I used to call them dotted, but somebody pointed out to me one time, those are dashes. Okay. Keeps going up, right? That's what the arrows mean. All right, so a number of things are going to happen here. You guys know from looking at this what the vertex is, right? It's in your standard vertex form, isn't it? So you know that the vertex is going to be 1 for h, the first coordinate, and then what's the second coordinate? -3, right? So this is what we talked about the other day. The vertex form of a parabola is a times x minus h quantity squared plus k, right? hk is the vertex, remember that? So 1 and -3, right? So in other words, if your final graph is going to look something like this, but it's going to be transformed. There's a couple of transformations we have to do. Eventually, we're going to have to move the vertex so that it goes to 1, -3, and we're going to have to take all the other points with it. You don't want to do that first, though, but just keep that in mind. What you're going to want to handle first is the kind of like with the order of operations, you want to handle what the multiplication does by -2. And then worry about shifting the graph so that the vertex is in the right place. Okay? So actually, the -2, we have to separate it. Multiplying by 2 does something, and then multiplying by a negative does something else. They're two different transformations. So, and it doesn't really matter what order you do it in as long as you do these two before you shift it left or right or up or down. So let's talk about what the 2 does. So forget about the negative. What does y equal 2 times x squared do to the original base function? So I'm multiplying 2 times the base function. Does everybody see that? The base function is y equals 2x squared. I'm multiplying 2 times all the y coordinates of the base function, 2 times x squared. So what is that going to have the effect of doing to all of these points I plotted? So x squared is the y coordinate of the base function. So if you multiply all the y coordinates by 2, how does that affect these points? The y coordinates of those points, rather. It makes them all twice as big as they were, right? And really, those are measuring distances from the x-axis. The y values measure distances from the x-axis. Does that make sense to you? So they're all going to be twice as high or twice as low if they were negative as they were when you started. So here, they're all positive, so they're all going to be twice as high. But if you had a negative, like a -2 as one of your y coordinates, it would go down to -4 if you multiply it by 2. Not a problem here. So that means that this point at 1, 2, 3, 4, at a height of 4 is going to go up to 5, 6, 7, 8 would be up here somewhere, right? This point would go twice as far as it is currently from the x-axis. This point would be twice. It's at a height of 1. It'll go to a height of 2. This point, height of 1, go to a height of 2. Okay, this point currently is at a height of 0. So if you multiply 0 by 2, it's still 0, right? So what does multiplying by 2 do? It stretches that base function by a factor of 2, doesn't it? It's a vertical stretch, that is. A vertical stretch by a factor of 2. So anyway, the graph in yellow here, and you could, again, do it dashed. It's just easier to draw on this thing with it solid. The graph in yellow here is what you get after you apply this stuff. So we color code it. That's the yellow part. Okay? Now let's handle the negative then. What will y equals -2x squared look like? In other words, the 2 is already taken care of. It stretches it by all the y coordinates of the original parent function by a factor of 2. So really what I'm asking you is, what does the negative do? Yeah, it makes, so remember what we did was we doubled all of these, right? To multiply by 2, we doubled all of these. So maybe I ought to do that in yellow to color code it. So 8, all the y coordinates were double what they were. So 8, 2, 0. 2 and 8, right? And so what is multiplying y equals 2x squared by a negative going to do? It's going to make them all negative. So let's see if we color code it red. In the yellow graph, all of the y coordinates, if you want to include the negative then, and what that transformation does is it then will make all the height values negative, so it has the effect of reflecting the yellow graph across the x-axis. And it doesn't change the absolute value of the y values. They'll still be the same distance from the x-axis, just in the opposite direction. So just visually then, this point right here is at a height of 2, right? When you multiply it by a negative, it'll go to a height of -2. Oops, I already used red. So I should have color-coded it differently. How about green? Okay, so there we go. This height was, this yellow point was at a height of +2. It goes to a height of -2. This guy right here was at a height of 0. What happens when you multiply 0 by a negative? Nothing, right? Stays. And then these points, if we were going to plot them, these points are at a height of 8. They would go all the way down to -8, but I don't want to go down that far. So I'll just draw part of the graph. And then it just, it just keeps going. So this is the graph. The graph of y equals -2x squared is in green, right? Does that make sense to you? So what did we do first? Well, this too, in this step, well, we plotted the base function first, but then the next step, the next first step, which would be the second step in most people's minds, we multiplied by 2, right? That was a vertical stretch. And the vertical stretch factor was 2. And then we handled the negative. The negative gives a reflection across the x-axis. It doesn't really matter which order you do steps 2 and 3 in, but you do want to do those before you move the vertex. Okay? So that graph in green is the shape of our final graph. It's just not situated in the right place. We know its vertex should be 1, -3, right? Which means there's 2 shifts going on. There's a horizontal shift, I'll call it an H shift, of +1. So in other words, I'm going to move that graph in green to the right one, the whole thing. Because if I move the vertex, I got to move all the other points as well. Otherwise, it's not the same shape anymore. And then there's a vertical shift called a V shift of down 3. So I have to move the vertex right 1 and down 3. I got to move the whole graph right 1 and down 3 is what I'm saying. So let's do that and then we'll wrap it up. So I'm going to try to graph, my final graph will be in blue, I guess. And I'll just take these 3 points that I plotted and move them right 1 and down 3. So the vertex right 1 and down 1, 2, 3. There's the correct vertex, 1, -3. This point, right 1 and down 1, 2, 3. This point, right 1 and down 1, 2, 3. And draw it so that it looks like the same shape as the graph in green. So you can think of 2 more translations. You could think of a horizontal shift or a horizontal translation. And that was given to us by the first coordinate of the vertex, which was just +1, 1 to the right, or just +1. And the vertical shift was that because of the negative, it was actually down 3, so you could write -3, right? Or down 3. Don't write down -3, because then it's kind of like 2 negatives in a row. So one or the other. And what we've just described here in this one problem is almost everything you need to know about transformations. Not everything. We'll talk about all the other stuff next time. But number 1, we plotted the parent function or the base function. Number 2, we talked about the vertical stretch. If it had been like a 1/2 instead of a 2 in front, it would have been called a vertical shrink. Number 3, we talked about the reflection across the x-axis caused by the minus in front. Number 4, we talked about the horizontal shift that we had to do, 1 to the right. And that's just picking the whole graph up and moving it to the right. And then the vertical shift, we did 4 and 5 all in one step, really, of down 3. That's a vertical shift. And we're going to find out next time that if you write any function using this sort of standard form idea, we have to do it inside of function notation. But if we write any function given a parent function y equals f of x, if we write it in this sort of format where we know what we're subtracting from x and we know what we're adding on the outside, so like what we're subtracting from x is h, what we're adding on the outside is k. If we know what those values are, if we know what we're multiplying by out in front, then you get whether or not there's a reflection, whether or not there's a vertical or stretch or shrink, or a horizontal or vertical shift, you get it in exactly the same way. So now let's assume that y equals f of x is just some base function, not specific. It's not the same function as in the above example. Then what's going to happen is this. So let's assume we take the base function f of x and we multiply out in front by some constant a. Not saying what A is. It's just some constant. And then inside the x values, we subtract off some value of h. H could be positive or negative. And then we add on some value of k. There's going to be transformations associated with each event. So let's take it one thing at a time. So if we multiply by a, then the absolute value of a is going to be the vertical stretch or shrink factor. If a is between 0 and 1, it's a shrink. Absolute value of a, that is. If the absolute value of a is bigger than 1, it's a stretch. So the absolute value of a is what I'll call the v stretch or vertical stretch factor. It could be a shrink, so I'll say vertical stretch / shrink factor. Again, if a is a proper absolute value of a is a proper fraction, then it's a shrink. If the absolute value of a is bigger than 1, it's a stretch. So why am I saying that? Well, compare it with what we have up here. With what we have up here, it's a mess now. A was -2. The absolute value of a was 2, which was the stretch factor. So I'm really kind of saying in general what we did up here specifically for this problem. Okay. If a is negative, that controls whether or not, think we had -2 up above, right? That negative controlled whether or not there is a reflection across the x-axis. So in case I didn't mention that a few minutes ago, this negative, I think I did, this negative, yeah, I know I did. This negative right here reflects the graph of y equals 2x squared across the x-axis. We went from the graph of yellow to the graph in green. So in general, I'll just say this. In general, I'll say if a is less than 0, then there's going to be a vertical, well, let's call it a reflection across the x-axis associated with the parent function. Then reflect, I'll just say this, reflect across x-axis. And then the thing we subtract from x controls the horizontal shift, left or right. So there's a horizontal shift, and a horizontal shift is h. If you don't insist that h is positive, then the horizontal shift, just the sign of h indicates direction. If h is negative, you shift to the left. If h is positive, you shift to the right. But there can be a confusion there. Look, if it's h is the thing we're subtracting from x. So you have to see a minus here for that idea to work. So if you see x, what do we have above? I forgot. If you see x minus 1, h is 1. So you shift positive 1 to the right, which is exactly what we did. Positive, oh yeah, the graph in green, or in blue rather, was a shift 1 to the right, and then of course down 3 of the graph in green. And then k, the guy on the outside, think about what k did up here. The guy on the outside gave you how far we shifted it up or down. In this case, you go with the sign. If it says -3, if k is -3, then you go down 3. So in this case, we would consider k to be, we would include the negative. So that k is going to give you a vertical shift, or translation, same thing. It's just shift is a shorter word, so I use that. Vertical shift, k units. And then I could have said h units here as well. So this little diagram I've created will help remind you of most of the transformations that we talk about in here. There's a couple more we still need to talk about.